Thank you very much for the kind introduction, and thanks for having us, and thanks for making the time being here. So we want to talk today about two pavilions we've done, as we call it, in integrated teaching and research projects with our students at TH Lübeck. And I want to make a short correction because Michael now moved to Bauhaus University. So if you try to find him online, you need to browse to the University of Weimar. All right. We've heard about this in the keynote. This is also why we do additive manufacturing and why we are running the RoboLab, because we want to create awareness amongst our students with these integrated research and teaching projects about these issues, which I don't want to go too much into detail. We talked about already the productivity and the manual labor cost that is involved in the construction sector, and we all know, and I think that's motivation for many of us, why we are trying to automate construction, and specifically why we look into additive or robotic fabrication. This is a project with a sort of a working title, Biopolymer Pavilion. Students were tasked with 3D printing as a starting point to create structures, basically to develop ideas how we could use 3D printing in real construction. So the task was for the students to think of something that actually can be built together with industry partners. The group of students that made this pavilion, they started from the material, so they looked into being sustainable by using biopolymer as a material, because it is part of the biological and the technical circle. You know all this, so we try to keep material as long as possible in the biological circle. When it comes to the technical circle, we then try to keep it as long as possible in the technical circle, and at the very end it then would need to go back hopefully into the biological circle. So the students looked into a torus, basically a half torus, and decided to do a part of it, the idea for the overall construction, because we were limited in size and capacities to do only parts of it. So the idea is to create a shelf structure, because we know that shelf structures are very efficient in their structural capacity. So students developed the geometry. They faced the typical problems, right? Tessellation, equal balance tessellation, and try to understand how they could actually create the pavilion. Again, right, so if you have a double curved surface, you might all be very familiar with this. There's this problem that you get doubly curved elements within this doubly curved surface, and because we had limitations in a flatbed printing production process, the students need to think about how to co-planarize the single elements so that they actually could be built. So they did this through, optimization, looking into how they could adapt these elements, and then because it was not printed as one, but printed in single segments, it was important to think about how these elements actually come together. Again, they needed to think of these coplanar connections between the elements vertically as well as horizontally. because we had to build this, and because the material was not very familiar to us and to the students, we actually used our material testing facilities to not test the material itself, but to look into the actual elements and the actual printed elements to understand whether at the end the pavilion would stand up or not. And we've already heard previous speakers talking about the tolerances and the accuracy of the 3D printing process, and also here that's a question basically that we try to make the students aware of, that what is very accurate in the virtual world, in the digital model, might not be as accurate as you print it actually in the physical world. Again, the testing, not only single elements, but also segments of the elements, and because not we are only interdisciplinary, but the students are also interdisciplinary, teams of structural engineers and architects. Then the production themselves, so we also make the students actually to go into industry and print the elements themselves, so they are on site and experience all the hustle, all what it takes to actually get a 3D printed structure out. Again, we talked about the inaccuracies. We learned, and in this pavilion, and the students, they provided a solution, so actually to transport the forces not through the actual printed material. We've seen that also, I think, in larger scale in other projects, but basically through the connection bolts, because the tolerances, because we weren't milling afterwards, the tolerances were too large to actually make sure that the forces are transferred. So this is the actual pavilion that we did together with the students. That's the team that actually built it up, and with the partners Weber Additive and UPM Formi that provided the material. It was quite, as always, not the achievement of one person or two persons, but the achievement of a very vigilant team. We try to, so this is a follow-up with a student from that group that actually took it further into real construction, and how we could use this this process, this principle, to actually do extensions on existing buildings in Germany. This was a master thesis, and actually with the student we're currently working on something that we actually would build in actually building scale.
Okay, so loud. Since I'm always also a partner in a structural design office, I'm always thinking about how to bring digital design processes out to the construction site. And we have architects and engineers working together on this large-scale building projects, and we're doing all the BIM simulations and finite element analysis and structural optimization, and we're able to optimize the amount of material, concrete and rebar when we are doing all this digital modeling, and we can simulate how things get built on site. And part of how we build on site, it's prefabricated to be fast to build, but still there are a lot of things still being built manual, and things on site haven't changed. Yeah, we've seen that in the first lecture as well, that concrete is still cast as it has been since 100 years. And of course, what could be a game changer bringing robotic fabrication on site is concrete 3D printing. We're all looking into that, and there are projects doing since a couple of years building houses. They're going now to multi-story houses actually bringing down the prices of that houses, which is a big topic, because it's not just about technology and that we can do this kind of things. It's also about building faster and cheaper. There is this interesting slide from Professor Otto from TU Dresden, and he had a look for an office floor with 600 square meter of wall space. And if that office floor is getting built with cast concrete walls, it would take 1,200 hours to build that walls. If we do it prefabricated, we could bring it down by half. If we do a full filled concrete 3D print with actual printer space, which is available, it would be 500 hours. And if it's sort of a optimized structure printing on site, it would be 300 hours. So you really can see how, and we're just at the beginning of 3D concrete printing on site, how we could bring down the work hours on site, which are really a big part of the overall cost of building. So in the next year, we gave the students a task to think about concrete 3D printing, and of course concrete is really good in compression. So the overall group decided on looking into a compression form-found shell, sort of a hanging model, compression only, and then we did the whole design process with them, doing the form finding in Rhino Kangaroo as a hanging model, and then transferring it to meshing it, looking at planarity of the elements, all these steps you need to have a look in when you actually want to go farther than just a student design project and actually be able to build something. Luckily, we have this group of around like 10, 15 architectural students and also structural engineering students, and they come together in this project and they need to collaborate on that. And the structural engineers had the task to do the structural design for this compression only shell structure, and it gave them quite a hard time, because in like traditional structural engineering education, they do masonry designs, pure compression, but not on sort of this free-form shapes. So it took us a while, but then they really came together and took the challenge and ran models and come up how they could design it and make the design checks. But they still weren't 100% sure if they could trust their calculations for the shell. So what really brought the next step was that we sort of printed a mock-up in our lab, and you can see that we have this 200 kilogram on one edge stone, and that convinced them that we could move on and trust our designs. Again, we had this really great partnership in that project with Vertico. Volker's here as well today, and he will be giving a lecture later on. And I think that really gives the students an insight on how we can bring these developments into industry if they collaborate with these companies and go to the companies. So actually it was over 100 individual stones, and we built it up for the Not Fair construction fair. It has a span of 6 meters and a thickness of 5 centimeters as a load bearing shell structure, and the curvature gets defined by the angle of the walls of the stones. This project got a lot of attention, and we were able to re-erect it at the state parliament in Kiel in Schleswig-Holstein for an exhibition on robotic building culture, doing the transfer to public interest. So from there on we took it to research proposal, and hope to be able to build that thing just 10 times the scale next time as a real project. Thank you very much.
So, thank you. Questions from the audience? Okay, then let me ask a question. You just said you had to reassemble it in front of the parliament, and when I'm looking at the left picture, I see some mortar in between the bricks. How much of an effort was it to tear it down, to remove the mortar, and to get it back, or was there any? So how did you do that?
We used some coating of the walls of the stones to be able to remove the mortar after the first erection. So that actually the second time it was much faster to rebuild it, and taking off the mortar grouts wasn't a problem at all.
Okay, cool. Because but it was planned to be disassembled and rebuilt.
Yeah.
So that was on an intention.
Yeah.
Okay.
So we have
the original idea was to use rubber between the stones, but we couldn't find actually quite a stiff enough and workable material to actually not use mortar. So the mortar really only served as the mitigation of tolerances, so that we get a continuous flow of forces, basically.
Yeah, rubber would have been my instinct too in that case, like that things you put under your washing machine so it doesn't vibrate. That would be my first go-to in such a case.
Yeah, thank you for the presentation. What is interesting here is you use a company, you use a service to do the 3D printing, which frees up space to think about the design and the structure of the thing. And I think it's super important because we educate architects and engineers, and they will not be the people printing the stuff, but they need to learn how to design these things which are worth printing. Do you have any thoughts, or what kind of experiences did you make? Did students take that into practice already, or are they still with you guys now doing research?
Well, I think one important step is that we have a RoboLab, so we do smaller prototypes on site with the students, and this is I think a very important step in not only in understanding but also in motivation of the students. Well, at least in my experience, the moment they've been into the lab, they've created, for example, one of the stones that worked or didn't work. They develop motivation, and they want to get into to the grounds of the process and get it actually done. So for me, I think it's very important to actually get them out of the classroom into the lab, and then certainly, then they realize, we can't do 102 stones on ourselves, and then we need to work with industries. And then again, working with industries, right? They have other boundary conditions. They are asking reliable information, data. I mean, there are very many levels of learning within such a design and build project. Definitely, yes.
All right. There's one last question from Massimo before we have to move on.
Thank you. Just a quick question. How did you assemble this thing in place?
You can see it in the background. So we sort of built a timber substructure and lowered it.
All right. Thank you.
Thank you.